Ave Coders. In this video, we're going to be building a complete machine learning pipeline. That is, we're going to read the data, we're going to clean it, continuous and categorical features, then we're going to break it into training, validation, and test sets, and we're going to save them. Then we're going to use the cross-validation to train our random forest model on the data. And finally, we're going to choose, with the help of the GridSearchCV, the best performing sets of hyperparameters for the model. Then we're going to test them on the validation set. And finally, we're going to pick the best model and we'll test its performance on the test set. And as usually, we're going to be writing this code in GoogleCollab notebooks. You can find a link to this notebook in the description under the video. So essentially, we're going to be repeating some of the material which you've already seen in the previous machine learning lessons on this channel, and we're going to be building on top of that knowledge. So here's our data set. We're going to be pretending that the training data set from the Kaggle, it's all we have. Nevertheless, in the Kaggle's case, it is broken into training and test set, but we going to be using just the training part of it. So Titanic train CSV, and let's count the missing values first. So we'll be using isNull method. It returns 1 as soon as it encounters a missing value, so NaN, and then we'll use the method sum to sum all these flags, all these ones where the missing values were. So age has 177 occasions of missing values. And in the exploratory data analysis lesson, we concluded that age is missing at random, that there are no patterns or explanations why age is missing. Therefore, we can replace these missing values with the mean value of that column or of that feature. That way, not only we fill in the blanks, but also we are not introducing bias into the data. Because if we would have filled the missing values with, say, the minimum value or the maximum value of that column, that would introduce the wrong perception for the model of what age of the passengers was. So with pandas, we're going to take this column age and we're going to use method fillNA, and we'll pass this column dot mean as an argument, and that should do the job. And also, because we want to introduce this change into the current data frame, we must specify a parameter in place and set it equal to true. Otherwise, it will simply create a new separate data frame. All right, now that we've done that, let's relaunch the previous cell where we are summing up the null values or missing values. And as you can see, now the age has no missing values. Jolly good. And we've also established that CBSP and Patch features generally follow the same trend. And since they represent generally quite common information, we thought maybe it's a good idea to combine them into one feature that we might call something like family. So to illustrate the commonality of CBSP and Patch, let's represent them graphically by iterating over them and creating a plot. And we're going to be using the Seaborn library categorical plot, known as catplot, to illustrate that. So for I, indices, and col, columns in enumerate, and then we specify both features, so CBSP and Patch. So in general, it illustrates that the more siblings or family members you had on board, the less chances you had to survive. So in terms of these plots, the x-axis will represent CBSP, and on the next plot it will be Patch, but y-axis will represent the survived target variable. But if you want to dig deeper and have more information on this subject, I would recommend you to watch or rewatch the lesson on categorical features. You can find a link to this lesson among many other useful links in the description. All right, so meantime, we've finished this code. Let's run this cell. And here we can see two plots for CBSP and Patch. And you can definitely notice that downward trend on both plots. So this basically justifies what we're going to do next. So below this plots in the next cell, we're going to combine these two features together. So we'll create a new feature, a new column. We'll call it something like family count. And let's make it equal to Titanic SIB-SP plus Titanic Patch. It's not particularly good to have several features representing the same information or even duplicate information. So we'll have to later drop this SIB-SP and Patch features, because otherwise it can create something that is called multi-collinearity, which is basically a concept where several independent variables in a model are correlated. So long story short, we don't want that, therefore we'll drop them too. And also the passenger ID, we also concluded that it does not really reflect any possibility of survival. It just a useless basically feature in our data set, therefore we'll drop it as well. And since we are dropping columns, we need to specify another parameter axis to be equal 1, and of course in place equals true. So we're not creating a copy of the current data frame, we are saving changes in our current Titanic data frame. And let's use the head method to show us 5 first records or 5 top records. All right, so since we have achieved some progress, it will be a good idea to save that progress. So that, for example, if we want to pack up for today and continue working on this notebook another time, we could actually continue from the same point or upload this data frame to another notebook or pass it to some other person. Anyway, it is a good practice to save our progress. So to save this file, we're gonna utilize the toCSV method, and all we need to do is to copy the path so we can save it to our Google Drive. So I'll paste this path to our toCSV method. It looks like I forgot the quotes, so we shouldn't forget them. And all we need to do now is to rename the file to something like Titanic Clean. And also another good practice is to set the parameter index to false. So if you look at the leftmost column, you'll notice this indices 0, 1, 2, 3, 4. So if we will not specify index equals false, then pandas will save it as a legitimate column. And next time we'll read this data frame, we'll get a useless feature. All right, so here is our Titanic Clean CSV in my Google Drive, and we can just check that it has all the information in it. Indeed. All right, so let's carry on working on our features. And if you remember, another column that had null values in it was cabin. But in our previous lesson dedicated to categorical features, we've established that cabin number itself was not influencing the survival of the passenger. What was important is that the passenger had a cabin. So those passengers that were traveling in a cabin had greater chances to survive than those who didn't have one. So instead of the column with cabin numbers, we can have basically a column which will specify whether passenger had a cabin or not. So 0, passenger didn't have a cabin, and 1, there was a cabin assigned to this passenger. So we'll call this feature cabin index, and we'll use the NumPy function where that will assign a value according to some condition. So in terms of understanding how it works, it is very close to the ternary operator, if then else. So the first is the condition. So if the cabin is null, so if passenger didn't have a cabin, then we'll assign a value of 0. Otherwise, meaning passenger had a cabin, we'll assign a value of 1. So this creates a new feature, cabin index, which is a column filled with values 0 or 1, depending on the condition, depending on whether passenger had a cabin assigned to him or her or not. Okay, so next feature we're going to binarize is sex. So back in Titanic days, there were only 2 sexes, male and female. So we can convert them to numeric values. So male will be assigned 0 and female will be assigned 1. So we're going to store that information in a dictionary called sex numeric. And in this case, instead of creating a new feature, we'll save it into the same feature, sex. And then we'll apply mapping of these values, male and female, 0 and 1, to the column sex. So now all we have to do is to pass this dictionary to the map function, run the cell, and now we can get rid of redundant features and drop those redundant unnecessary columns. So in the next cell, we're going to do more cleaning. In fact, this is going to be our last cleaning before we'll actually start splitting this data set into training, validation, and test sets. So we'll use the drop method, and we're going to pass a list of the columns we want to drop. In our case, this is going to be cabin, embarked, because we concluded that it doesn't matter which port was the port of embarkation per se, the name of the passenger. So unless the passenger called Aquaman, it probably wouldn't have to survive in cold waters. And the number on a ticket is not as relevant as the class of that ticket. So we can drop ticket as well. And of course, we need to specify that these are columns. So axis equal 1 and in place equals true. And now let's have a look at our clean dataset, titanic.had. So it will be pretty compact, but these are the relevant features. Okay, now we can go ahead and save this dataset. We already know how to do that. In fact, I can just copy and paste this line. So I will not be renaming a file. I will leave it as Titanic clean CSV, and I'll run the cell and I'll save this dataset. And we also know how to read the data. So let me just reiterate that once again. So we can pretend that someone else has cleaned the data for us and saved it into Titanic clean CSV. And let's say that we want to start from this point, and all we need to do, we need to read that CSV file, and read CSV method from pandas will help us to do that. So I'm just going to copy the path to the file and the name of the file. And also let's print first or top 5 records. So Titanic had. Let's just make sure that it is the data set that we intended to read and work on. All right, so now we can begin splitting our data into training, validation, and test sets. And just as a reminder, we want to allocate 60% of our data to be in the training set, 20% for validation set, and another 20% for the test set. So what we're going to do first, we're going to drop the survived column because survived is our target variable. So this is something we ideally want to predict. So when we dropped our survived column, we're going to save this data frame into features. And therefore, this column we just dropped survived will represent our labels. So once again, if you want a little bit more in-depth explanation, I will leave the link in description on the lesson where we do the train test split and where I explain why we split it that way. But one thing to mention is that scikit-learn cannot break the dataset into 3 datasets in one go. So we'll have to do that in 2 steps. The first step, we're going to take our features and labels and we'll break them into training and test sets. 60% to the training set and the rest to the test set. And then we'll break the test set half and half into validation and test set. But of course, we'll need to import this train test split method from the scikit-learn library first. So in that cell where we've done all the imports, below that, right, from sklearn, model selection, and we're going to import train test split method. Don't forget to run that cell again to finalize the import, otherwise it will not import anything. All right, so let's get back to our cell and we shall carry on. So in our first train test split method, we're going to pass the features and labels. So these are going to be our inputs. And we also need to specify values for a couple of parameters. First of all, we need to specify the size of the test dataset. So we pass 0.4 to the test size parameter. Because once again, we want our training set to comprise of 60% of the data, and then the rest will go to the training set. And then the random state parameter will receive a value of 42, because it is the answer to the ultimate question of life, the universe, and everything. But once again, we talk more in depth about all these parameters and methods in a video dedicated to the splitting our data. I'll leave the link in the description. All right, so the next train test split method will take the data we put aside for our tests and validation sets. So it will literally take this test data set from the previous train test split and split it in half. Therefore, we need to pass for the test size parameter value 0.5 and specify x test and y test as our inputs. And we would also need to adjust our outputs accordingly. So instead of x train, x test, y train, y test, we're going to have x test, x val, y test, y val. And the order is very important. So once again, we take the test set from our previous split and we split it in half into validation and test sets. So in the end, we're going to get 3 data sets: the training data set, the validation data set, and the test data set. So let's check that the split has performed how it should have performed and we get the results we expect. So to confirm that, we're going to iterate over the labels of our data. So the Y's, the Y train, Y val, and Y test, because they are 100% will be consistent. And what we need to do next is to divide the total length of our data divided by the length of our labels. That way we can construct the ratio of how much training, validation, and test data we have. So I'll remind you, we should get 0.6 for training, 0.4 for validation and test, so 0.2 for validation, 0.2 for test, and altogether that should be equal to 1. And of course we need to round that. And let's run this cell. And we can see that it was confirmed. All right, and now that we have 3 clean data sets, it is a good idea to save them that way, so that in the future we can upload them, all of them or some of them, as we require. For instance, to use them as inputs in some future methods. But the principles are exactly the same as when we were saving a single data set. So let me copy that line and I'll paste it a few times in this empty cell. The only thing is I'll need to change the names of the data sets we are saving and the names of the files as well. So we'll have 3 lines for xtrain, xval, and xtest, and 3 lines for ytrain, yval, and ytest. So I'll group features together and labels together so that it is easier to read and to see what's where. And plus, we are setting the index parameter to false because we don't want this column with the consequent indices saved as a feature. And once we've done with renaming, we'll run this cell to make sure these datasets are saved. And now when we have this clean and split datasets, we can get on with the cross-validation. There is a whole lesson dedicated to the cross-validation, so link is in the comments. But long story short, we break our training data into k faults. So in our case, that will be 5 faults. We reserve 1 fault for validation and we train our model on the remaining 4. Then after training on the remaining 4, we evaluate the model on this validation piece and we keep the score. We repeat this process 5 times, each time switching which fault is used for validation. All right, so in our imports, we can import cross-val score from sklearn model selection, and then we also need a model. The model will be Random Forest Classifier, and it's going to be imported from sklearn ensemble. We're going to have a separate lesson on random forest machine learning algorithm, but for now, just accept that it is something, a classifier that is used to classify or predict whether the passenger will survive or not. And in this particular lesson, we're not tasked with the actual prediction. All we want is to go through the whole pipeline and to check how this algorithm is actually performing on our data. So in essence, Random Forest is a classifier that contains a number of decision trees on various subsets of the given dataset, and it takes the average to improve the predictive accuracy of that dataset. So for the cross-validation, or 5-fold cross-validation to be exact, we are going to use the training data and nothing else. So all we need to do is to import our training features and training labels. After that, since we've already imported the Random Forest Classifier, we can instantiate it and we can call it RF. And for the time being, we're going to run it with the default values. Therefore, we're not going to pass any values for any parameters or hyperparameters inside those brackets. Below that, we declare cross-val score method and we pass our F as the classifier, then as data we pass train features and train labels, and CV, or number of faults in the cross-validation. So the value for this parameter will be equal to 5. And we save the output to the scores variable. And if we'll run the cell now, we'll get into a slightly annoying warning from scikit-learn. As you see, we actually get 5 warnings because we are running this cross-validation 5 times. It basically says that in terms of Ys, in terms of our labels, the sklearn expects a 1D array while it gets a column vector. So we'll need to apply a little bit magic to get a workaround. So all we need to do, we need to get to our train labels and type in dot values and dot ravel. And don't forget the brackets because ravel is a function itself. And that should transpose our labels and turn them into a 1D array that is expected by the cross-val score. And when we run the cell once again, we get no warnings. Okay, so let's check out the scores. We had 5-fold cross-validation, therefore we'll have 5 scores. So I'm anticipating an array of 5 values. And now basically we can take the mean value of this 5 values and use it as our final score. And as you can see in this array, we have scores varying from 0.78 to 0.83. And as you can imagine, taking the mean of 5 values is much more illustrative than if we would have, for example, just one attempt and one score. And now we can begin to fine-tune the hyperparameters for our random forest classifier and observe how our results change depending on what values do we assign to these hyperparameters. So like I've already mentioned, for the first run, we didn't pass any values for the hyperparameters and our random forest classifier was using just the default values. And let's see how the results will change when we'll start to pass values and specify these hyperparameters. So let's start a new chapter here. I'll insert the text cell and I'll specify hyperparameter tuning. And you can imagine that passing different values for different hyperparameters to this classifier by hand is a bit tedious. Therefore, we're going to import a function called GridSearchCV from sklearn. That will do the job for us, and we can import it from sklearn model selection. So GridSearchCV, let's run that cell. Now it's imported. Let's copy over this random forest classifier once again, so I wouldn't need to sort of scroll up top. All right, that is not a necessity. I just want everything to be grouped together. And in the same cell, I'll specify a dictionary. I'll call it hyperparams, which will contain hyperparameters and possible values for them. So hyperparameters, their type will be key and values will be, well, values. So in particular, we're interested in several hyperparameters. So 2 to be exact. The first one is the number of estimators. As I've mentioned before, random forest classifier consists of an ensemble of the decision trees. Therefore, the first hyperparameter is responsible for the number of decision trees we use in our random forest classifier. And we'll use 4 values. First one is 5, then 25, then 50, and 100 of decision trees. And the other hyperparameter is max depth. That represents the depth of each tree in the forest. Effectively, the deeper the tree, the more splits it has, and it captures more information about the data. And so the question is, what would prevent us from having a tree with a depth of 10,000 that would definitely sort of capture all information about the data? Well, the answer is overfitting. Here we specify the depth of 2, 12, 24, and none, where none, it means that nodes are expanded until all leaves are pure. And we say that a leaf is pure when all of its data belongs to a single class. Or in other words, all its data points contain the same label or cannot be split any further. Good luck digesting that, but meantime, we'll pass this RF Random Forest Classifier and hyperparams and also the number of folds to our GridSearchCV. And we can save this GridSearchCV function with its parameters to the cross-val variable. So that now on the next line, we can call a fit method on this cross-val variable, passing train features and train labels.values.label as arguments. So I'll just copy them from the cross-val score method. And if we run this cell, the output will tell us basically nothing. So it just lists something we already know. So we'll have to write a custom function that will actually print the results in the way we could actually read them. So let's call this function results. So basically we'll accept this cross-validation results and we'll print optimal hyperparams. To do so, we'll need to access the best params property on results, and we also want to print the mean value of those scores together with the standard deviation. And we get to them utilizing the cross-val results together with the mean test score and standard test score. Then we just iterate over them and print the results. And after we'll finish this function, we will be able to use it to illustrate the results of our random forest classifier with different hyperparameters with different values. So in the new cell, we'll just call this function results and we'll pass our cross-val there as an argument. Like so, and we get into an error. The error tells us that there is no attribute cross-val results. But that's not the end of the world because scikit-learn works from the box. I might have just put the wrong name of this attribute somewhere. So we just head to the GridSearchCV documentation. And here I see that we have CV results. And it's definitely not how I called it from the top of my head, cross-val results. So we just replace this attribute. So that is not a problem. I'll quickly replace cross-val results onto CV results. Let's run that cell and we'll try to call that function again. The same error. All right, so the loop should have its cross-val results replaced as well. So I'll just copy and paste. That's it. So I'll launch that cell. Let's call it again. Tuple index out of range. And whenever I think of this error, tuple index out of range, I think about brackets. GoogleCollab provides auto-closing brackets, and sometimes they can close where you don't want them to. So we just need to check that all the opening brackets do close where they're supposed to. And as we can see here, we have one bracket that's not supposed to be here. It's supposed to be closing the whole expression. All right, so let's relaunch the code And here we can see the optimal hyperparameters, max depth of 12 and number of estimators or trees 50. But bear in mind, yours might be slightly different. So I'm just showing the principles. So if we'll find the line with these hyperparameters and look to the left, we can see that it has a mean score of 82% or 0.82. So this is the mean score of 5 scores we obtained from 5-fold cross-validation. And if we look at the line below, we have exactly the same score, but the hyperparameters are different. We still have max depth of 12, but number of trees, number of estimators is equal to 100. And the reason why this set of hyperparameters was chosen as optimal is that because if we can get the same score but with less estimators, then this is a more efficient solution. So what we're going to do next, we're going to take 3 sets of hyperparameters with the highest scores. Then I'll define 3 random forest classifiers and I'll use this hyperparameters with them, and we'll apply that to the validation set to see what is the highest return, which classifier will have a top score. I'll call them RF1, RF2, and RF3. And once again, your sets of hyperparameters, your values for these hyperparameters might be different. All right, so check the mean. In your case, what is the top score there, and choose the 3 top sets of hyperparameters that give you 3 top scores. If you have an even score somewhere, don't worry, just pick 3. It doesn't matter really. All right, so once we've got that, we need some kind of a metric to measure the performance of this classifier. And since this is a classification task, there are 3 basic metrics that can help us. So one is accuracy, the other is recall, and the third one is precision. So accuracy is how many cases we predicted correctly to the total number of predictions. Precision is how many passengers we predicted will survive and actually they survived to the total number of predicted to survive. And recall, this is how many passengers we predicted will survive and they actually survived to the total number of those that actually survived. All right, so now let's implement that in code, and scikit-learn makes it easier than you might anticipate. So we'll iterate over the classifiers RF1, RF2, and RF3. And for each classifier, we'll invoke the method predict, passing validation features as an argument. So these are the outcomes we're trying to predict. Therefore, we'll save it into ypred variable. So I'm passing val features here. And it looks like I missed the comma between RF2 and RF3. So I'll quickly correct that. Okay, and after I've done that, we can start writing code for our metrics. So the accuracy comes first, and here we don't need to write that ratio as you've seen on the slide. Scikit-learn takes care of it for us. So all we need to do, we need to pass this accuracy score, and that is it. We then pass our validation labels, and then what we're trying to predict, and then what we actually predicted. And we also will round that to 3 decimals after the comma. Next is precision, and similarly, we just change accuracy score to precision score, and everything else remains the same. And the last one is the recall metric, which is exactly the same as accuracy and precision. We just change the name of the method, but because I love typing, I will retype it manually. So recall score, and then we pass val labels, ypret, and then we round it to 3 decimals. And after that, all we do is we create a representative print statement where we display with placeholders the max depth, estimators, accuracy, precision, recall, and then inside the format we will specify variables and attributes. Their values will fill this placeholders once this print statement and the cell is executed. But just before that, we'll need to address those warnings, those underlined methods we have in code. So the first warning we'll need to address is the val features. And the way to do that is just to copy those lines that read train features and train labels from the CSV files and expand them to the validation features, validation labels, and also for later, we'll do the test features and test labels as well. So I'll just copy the ones that we already have, train features and train labels, and I will just paste them here. And I've put the header none, and I'm not quite completely sure whether it will work with or without it, so we'll test that later as well. All right, so now it's the time to address our metrics. So here, where all imports are, on a new line, we write from sklearn metrics, and then we import accuracy score, precision score, and recall score. This will clear the warnings, and then we'll finally be able to run that cell and observe the scores. And then we'll pick the best classifier out of them 3 and we'll run it on a test set. So let's run that cell, and we get into an error that it found input variables with inconsistent number of samples. And here you can see we have a parameter header none. So this is something that is causing that error. So we need to remove all of them from the validation and the test as well. And from here on, we can actually go to the runtime and select run after. So that will run the current cell and all cells after the current cell. That way it will accommodate all changes in all cells below, and that should take some time when we do the fitting again. And now, and if I'll scroll down below, please ignore the last 3 cells. This is something I was testing. So as you can see, these are the scores, and the first classifier, RF1, has the top accuracy among all of them. In your case, this might be different. RF1 classifier has also got the top precision score and also the top recall score, sharing that with the last classifier. So RF1 is clearly our pick. So these are the results of performance of these classifiers on the unseen data, the validation set. Now we can take the RF1 classifier and use it on another set of unseen data. This is going to be the test set. So I'm copying the code from the cell above, but because we have only one classifier this time, we don't need the loop. And I also need to replace that variable I've used for iteration, MDL, onto the RF1. And of course, all val features will be replaced with test features this time. And again, in my case, this is the classifier number 1. In your case, this might be a different classifier. So you might want to use a different variable, but in my case, this is rf1. And I also need to change this mdl to rf1 inside of that print statement. So rf1 max depth and rf1 number of estimators. And now we can run that cell and see the score on the test data. So here we can see that we have accuracy 0.79, which is not too bad. Precision is slightly lower than when we tested this on validation set, but still is a pretty decent result. And recall is slightly lower as well, but again, not too bad. So this basically illustrates what we can expect from the model with this set of hyperparameters. So now we can use it to make predictions. All right, so congratulations to those who made it up to this point. We have experienced the full machine learning pipeline. We imported the data, we cleaned the data, we got rid of the features that were redundant. After combining some features into a single feature, then we split the data to training, validation, and test sets, and we saved them on our hard drive. And then we've also learned how we can load them separately as we need them. High-level overview, how the Random Forest Classifier works, how k-fold cross-validation is performed, then how to use GridSearchCV to find the optimal hyperparameters, and how to use the metrics, accuracy, precision, and recall, then how to choose the optimal classifier and how to use that classifier on the test set. Next, we'll dive into how the machine learning algorithms work, linear regression, logistic regression, k-means clustering, and many others. But meantime, please give this video Emperor's thumbs up, toll the bell, and subscribe. That was V, and I'll see you in the next lesson. Bye for now.